In this lecture, I'm going to continue our discussion on the different type of resistive transducers, and here two types of resistive transducers for temperature measurements are going to be discussed. So the first one is the resistance temperature detector (RTD), which is also known as resistance thermometer. So RTD is normally uses a metal conductor, and the resistivity of that metal conductor varies with respect to temperature, and with respect to that the value of the resistance of the metal conductor also changes, which is used to determine the temperature. Now the variation in resistance with respect to temperature can be represented in terms of this higher order polynomial, because the relationship at higher values of temperatures becomes non-linear. So it is represented by this non-linear equation. Here R0 represents the temperature of the resistance at 0 kelvins, and alpha 2 and alpha 3, these are actually the coefficients associated with each higher order term, and R is the resistance. uh, R is the resistance determined at a particular temperature T. However, as the relationship is nonlinear, to make the calculations easier for a particular temperature range where the relationship can be considered to be linear approximation is done, or in some cases for higher accuracy, quadratic approximation is also done. Now, the materials that are going to be used to construct the RTDs, they should have some desirable characteristics that will allow the measurement done by the RTD to be accurate. So what are those characteristics? That is the change in the per unit, change in the resistance with respect to the per unit change in temperature should be as large as possible. So which means that the sensitivity of the material to the change in temperature should be as high as possible. So even for smaller changes in temperature, if the rise in resistance is higher, then uh, small changes in temperature can be detected with higher accuracy. Then the second point, that is the materials should have high resistivity, so that a minimum volume of material is used for the construction of RTD. So for example, suppose at 0 degrees Celsius, we want the resistance of the RTD to be 100 ohms. So if a material has high resistivity, we can have this 100 ohms with the smaller volume of that particular material. But if the material has a low resistivity, then to have the same amount of resistance, a larger volume of the material will be required. So if larger volume is required, then the size of the transducer will also increase. And if the same resistance can be obtained using a smaller volume, so the size of the transducer can be reduced. The R versus T graph, or the relationship between R and T, should be continuous, stable, and repeatable. So there should be a continuous and a stable relationship. So if the relationship is abrupt, or there is oscillation between the relationship between the two quantities, then a straightforward relationship between the two quantities cannot be established. And the graph should also be repeatable, which means that suppose for a particular instant, at 0 degrees Celsius, a value of the resistance is 10 ohms. When the temperature rises to 5 degrees Celsius, it becomes 12 ohms. Then at 10 degrees Celsius, it becomes 15 ohms. So this pattern should be repeatable. And suppose from 10 degrees Celsius, when the temperature decreases to 0 degrees Celsius again, it should go back to 0 ohms again. Then again, for each jump in the value of the temperature, the jump in the value of the resistance should also be similar for each case, which means it should be repeatable, so that the relationship between two quantities can be justified as a uniform relationship. Now, for some commonly used metals, the I mean uh, graph between the change in resistance with respect to the change of temperature is shown over here. So the commonly used materials are the platinum, copper, and nickel. So looking at this graph, you can say or determine one of the advantages of platinum, that is it has a linear range of operation which is higher compared to the others. So for a wide range of variation in temperature, platinum will give a linear relationship, whereas copper and nickel, they go into a non-linear state of operation at relatively smaller temperatures. So these are two this is one disadvantage of copper and nickel with respect to platinum, but they also have some advantages over platinum. That is, you can see that the temperature coefficient of copper is higher with respect to platinum, because for a small uh, uh, I mean for a small amount of rise in temperature, the fractional rise in resistance is higher in copper, which means that the temperature coefficient is higher, and for nickel it is even more higher. So nickel and copper is showing a higher sensitivity as the temperature coefficient is higher than platinum. However, a trade-off has to be made so that a wide range of uh, I mean temperature can be covered for wide range of application, and also at the same time a relatively acceptable accuracy can be maintained. So, and one more thing is that in most of the cases for RTDs, uh, different types of metals are used, and almost all the metals have a positive temperature coefficient, which is that with I mean with the increase in temperature, the resistance of each of the materials will also increase. So if I go to the next slide here, there is a summary between the three the three metals which were shown in the graph of the previous slide. So the temperature range up to which the three metals can be operated with satisfactory accuracy is defined over here. So you can clearly see that the range of operation for platinum is definitely higher compared to the other two. And in terms of the resistance and temperature relationship, the platinum has the best stability, and it also has a good linearity, because for a wide range of temperature, it has a stable relationship between the resistance and temperature, and also it has a linear relationship. Now, copper has best linearity compared to the three. Now it might be a bit confusing, because if we go to the previous graph, you can say that okay, copper is having a linear relationship up to this, but after that it is going into the non-linear state. Then how can it have the best linear best linearity? So it is not considered for the entire range, but for this particular range where it is linear, it is showing a better characteristics compared to the other two, because you can see that the line, this straight line, is almost at a 45-degree, which you can say that it is a one-to-one relationship between the change in resistance and the change in temperature, whereas the line of platinum and nickel is deviating from this 45-degree line, And if you have, suppose, a 45-degree line, suppose x and y, and there is line at the 45-degree, if they are scaled at the uh, uh, same interval, suppose 1, 2, 3, then if the line is at 45-degree, then you can have a one-to-one relation. So this point, it will have the same value at y and same value at x. So with respect to that, for this particular range, copper is termed to have best linearity compared to the other two. Nickel also have some advantages. It has a low cost. Copper also has a low cost compared to platinum. Now another advantage of nickel is it has high sensitivity compared to the other two. You can also justify that from the temperature coefficients that are mentioned over here. So you can see that the temperature coefficient is of nickel is high compared to the other two. However, their application is limited because of the limited range of temperature, whereas platinum is widely used because of their wide range of uh, wide range of linearity. And another advantage of platinum is that they, as a noble metal, it shows very limited susceptibility to contamination. So it withstands its pure quality for a long duration. So the other metals that could be used, so those are gold and silver. However, they are rarely used because of their high cost, and also they have low resistivity. So for those disadvantages, they are rarely used. Tungsten has significant advantage over all these three metals. That is, it has very high resistivity, and also it has high sensitivity as well. So the uh, for high temperature applications, it is really effective. But for low to medium range applications, it is not frequently used because handling of tungsten is difficult because of its brittle nature. So for high temperature applications where it will not be where the range is beyond the range of platinum, copper, and nickel, the tungsten is a very suitable option. Now, it has been already mentioned that copper has low resistivity compared to platinum and nickel, although it has the advantages of linear relationship up to some range, and it also has a low cost. However, due to low resistivity, you know that a larger volume of the material will be required to obtain a specific value of resistance, so which will increase the size of the transducer. But for economic operations, if uh, cost is an issue, then it could be an economic alternative to platinum or nickel. But mostly these two are used for constructing RTDs. And a basic construction of RTD can be represented here in terms of this figure, where the metal winding is done across a non-conductive ceramic frame, and that is protected by an outer casing, and there are two connecting leads available to connect it with outer circuit, suppose a Wheatstone bridge, to measure the value of the resistance. Okay, and this is a practical figure of a practical RTD, where this long cylindrical shape you can easily suggested inside this protective chamber there is the winding of the resistive material. Then from the winding through this chamber, uh, in terms of these wires, the connecting leads are available for connection. And in order to mount this transducer in a particular chamber or a container or inside a pipe, some arrangement is there for mounting the a transducer into an industrial application area. Now moving on, like I said, that as the relationship between the temperature and the resistance is non-linear, so for having I mean or for doing the calculations easily, linear approximation is done within a particular temperature range where the relationship can be said to be linear. So suppose this is a non-linear graph between R and T, and suppose for this particular range we can consider the variation to be linear. Suppose the lower bound is theta1 and the upper bound is theta2. So for this particular range of the temperature, we can have a linear approximation of the relationship, which is done by this relation. So R theta is the approximate resistance of the material at temperature theta degrees Celsius. R theta 0 is the approximate resistance of the temperature at the temperature theta 0 degrees Celsius. So what is the theta 0 degrees Celsius temperature? It is actually the mean value of the lower bound and the upper bound. So for this case, you can say it is theta 0, which is theta 1 plus theta 2 divided by 2. So at this temperature, the resistance is R theta 0, and the temperature coefficient at theta 0 is defined as alpha theta 0. So this alpha theta 0 can be considered to be the temperature coefficient at temperature theta 0 degrees Celsius, and delta theta indicates change in temperature, which is theta minus theta 0. So in this particular case, the unknown quantities are R theta 0 and alpha theta 0. So for a particular for a particular range of operation from theta 1 to theta 2, if these two values can be determined, then expression for R theta 0 can be developed, where for different values of theta, the value of R theta can be easily determined. So in the next slide, in terms of an example, we can easily uh, uh, I mean uh, have an idea about it. So in this example 25.21, which is taken from the book of Shawnee, so you can see that there is a nonlinear line, and a linear approximation of this line has to be made between these 2 points, which is from 30 degrees Celsius to 60 degrees Celsius. So theta 1 here is 30 degrees Celsius and theta 2 is 60 degrees Celsius. So the mean between the two, theta 0, we can easily determine it to be 45 degrees Celsius as done over here. Now from this graph, for these corresponding values of the temperatures, we can have the values of the corresponding resistances on the y-axis, which is also defined over here, the 3 values at the 3 different temperatures. Now R theta 0 is known, but alpha theta 0 has to be calculated. So for calculating alpha theta 0, we can refer to the previous equation which is shown in the previous slide, which was for R theta 2. I am writing it R theta 2 into R theta 0 into 1 plus alpha theta 0 theta minus theta, it will be theta 2 minus theta 0. Based on this equation, and for R theta 1, we can write it to be R theta 0 into 1 plus alpha theta 0 into theta 1 minus theta 0. Now if you subtract r theta 1 from r theta 2, these two equations, if you subtract and solve for alpha theta 0, you can easily simplify and find that r theta 0 can be represented as 1 by r. Alpha theta 0 can be represented as 1 divided by r theta 0 into r theta 2 minus r theta 1 divided by theta 2 minus theta 1. So here this term is nothing but the slope of the line, straight line that has been approximate straight line that has been considered for this particular example. So the slope of this line. So the relation of alpha theta 0 is also given over here. So you know the values of these resistances, the temperatures, and also r theta 0. So you can easily calculate the temperature coefficient. And once you know the temperature coefficient, then you can formulate the general relation of r theta for this particular straight line. And for now you can put different values of theta and calculate the values of the resistance at that particular temperature. On the other hand, suppose you don't, your goal is to determine the temperature theta, then you can determine the resistance R using some mechanism which can be even by measuring by Wheatstone bridge. And once you know the resistance, then you can easily solve for the temperature as well. So in the next slide, a similar thing is shown. Suppose you don't know what is the room temperature, but you use by connecting the RTD in a Wheatstone bridge circuit, you can determine the resistance of the RTD at temperature T. Now, if you have a linear approximation already available to you, then you can put the value of RT over there, and with respect to all the known values, you can calculate the approximate value of the temperature theta. So in this way, by using a bridge circuit, you can determine the value of the resistance, and using the help of the equation with the in terms of the known values, the temperature can be also determined. As the relationship is non-linear, a more accurate approximation would be the quadratic approximation. So often, instead of considering only the uh, I mean, uh, instead of considering the only the linear fractional change in resistance, the quadratic fractional change in resistance is with respect to the change in temperature is also considered for the quadratic approximation. So here the notations are same as before. However, this extra term is added, and due to that extra term, an extra coefficient will also get added. So the alpha 1 is actually the linear fractional change in resistance per degree Celsius in temperature, which is similar to the the temperature coefficient that we studied for the linear approximation. And alpha 2 is the quadratic fractional change in resistance due to per degree square change in temperature because of the square which is present over here. And for this case, the unknown quantities are 3, that is r theta 0, alpha 1, and alpha 2. Whereas for linear approximation, there were only 2 unknowns. However, still for a particular range from theta 1 and theta 2, two quadratic equations can be written, and by comparing the two quadratic or simplifying the two quadratic equations to have an equation of two unknowns, two equations of two unknowns, those can be easily solved. So the two unknowns would be alpha 1 and alpha 2, because r theta 0 can be obtained from the graph or a data table. So with respect to the known value of r theta 0, two equations can be written, and those two equations with two unknowns alpha 1 and alpha 2 can be solved to find their values. Then once these three values are known of r theta 0, alpha 1 and alpha 2, then the generalized uh, quadratic approximation can also be formulated. So a similar example for this is given in example 25.22. So I want you guys to go through that example, then your idea would be clear about the determination of these three unknown quantities. So once these three quantities are determined from the linear quadratic approximation, the unknown temperatures can also be it can be solved for unknown temperatures as well and unknown resistance as well. Okay, now if we talk about the application of RTD, then some of the applications of RTD could be in high industrial applications where high temperature measurements are necessary, because in most of the industrial applications the processes are dealing with high temperatures. So uh, for those cases RTDs could be a good option to measure the temperatures. And you know that for high temperature measurements, suppose like it is shown over here, suppose for a 250 degrees Celsius temperature process, suppose you are measuring using RTD, uh, the measured temperature is 248 or 252. So compare, as the value is high, compared to this high value, the errors are not uh, that significant if you uh, compute the fractions of the error or percentage of the error, so that will be minimum. So for high temperature applications, the RTDs can be easily used, and even for low temperature applications, they are quite useful, because uh, the temperature ranges have been tabulated previously in one of the previous slides. So from there you can say that up to a certain extent for low temperature applications, the RTDs can also be used. And another example, suppose in a bioreactor where the cell, a continuous temperature has to be maintained, so for the proper and controlled growth of the cells. So for continuous monitoring of the temperature in that particular bioreactor, RTGs can be placed, or any other temperature detectors can be placed to continuously monitor the temperature. Now the other type of resistive transducer that I want to discuss in today's lecture, that is the thermistor. The principle of operation is almost same for RTD and thermistor. However, the slight differences are that in case of RTDs where metals are used to construct the RTDs, in case of thermistors, they are mostly constructed using semiconductor materials. And most of the semiconductor materials possess negative temperature coefficient, so which means that when the temperature increases, the resistance decreases. Some of them possess positive temperature coefficient, but mostly for thermistors, uh, the materials which are used, they possess a negative temperature coefficient. But why do we need to go for a negative temperature? I mean, thermistors which have negative temperature coefficient, because they have very high sensitivity compared to RTDs, because the temperature coefficient is I mean the negative temperature coefficient is the magnitude of the negative temperature coefficient is high. So for small changes in temperature, the uh, I mean change in resistance is also relatively higher, although the value is decreasing, but the change is higher. So suppose the graph is non-linear, but it would be a steep graph. So for each uh, small changes in temperature, the changes in resistance will be higher. So as the for small changes in temperature, change in resistance is high, so the sensitivity is also higher. And compared to I mean RTDs, another advantage is that they are low in cost, and as they are made of semiconductor materials, their size is also relatively smaller. So here is a typical graph of a negative temperature coefficient thermistor. So you can see that the temperature is not varying in a wide range. Within a smaller range, the change in resistance is very significant, because from the y-axis you can consider the jump from one point to another, and you can see that the change in resistance is really high compared to the change in temperature. Now, the relation between uh, the resistances at different temperatures can be approximated through this nonlinear equation, where RT1 is the resistance at temperature T1, RT2 is the resistance at temperature T2, and beta is actually a constant depending on a particular type of material which is used to construct the thermistor, and the typical value for beta lies within this range of 3500 degree Kelvin to 4500 degree Kelvin. So using this I mean nonlinear relation, the I mean quantities of resistances at different temperatures can be related. Now, for simplicity of the calculations, for the case of thermistor as well, for a small range where uh, I mean the nonlinear graph can be considered to be linear, similar to what we did for RTDs, a linear approximation can be made for that small range of linear operation from theta 1 to theta 2. And normally the thermistors which have a negative resistance temperature coefficient, the typical value for the negative temperature coefficient is 0.5 per degree Celsius, although it's a negative quantity. But if you compare it with the temperature coefficient of platinum or nickel or copper, you'll see that it is if you consider the magnitude, it is relatively higher compared to those materials. Now, the various shapes and available shapes and sizes of thermistors are shown in this figure. So this is a rod type construction, this is a bead type construction, and this is this type construction, and they are of very relatively smaller size compared to RTDs. So let me conclude here today. So just a brief introduction regarding the two types of resistive transducer that can be used to measure temperatures. So in order to measure the temperature, the particular transducer can be connected in a bridge circuit, and the resistance can be measured. If the resistance is known, then from the approximation equations, either linear approximation or quadratic approximations, the unknown temperature can be determined. And also, uh, suppose in the relationship can be I mean used in inverse form. I mean for a particular approximate equation, in that equation different values of temperature can be inserted, and the expected values of the resistances can also be determined. So in our next class, we will start our discussion with variable inductance type transducers, and also we'll try to discuss about different type of capacitive transducers. And later on in our discussions on transducers, we will also try to have some introduction on different type of optical transducers as well. Okay, so and I would like to conclude today's lecture to this, and next class we will start from here on.